Okay. Uh, all right. You might as well start. Well, how are you, first of all?
Okay. It's a
Okay.
Friday.
It
It's a
is
Friday.
Friday. That's a good thing. That's a good thing. Um, yeah, and I still need some work from you. You know that.
Yeah. I'm
Okay.
gonna try and finish it tonight.
Okay.
Just yeah.
Um, so we have a quiz
Yeah.
um, on eCollege. It's quiz four, and the password is all small letters isosceles. Can you spell that?
Yeah.
Okay. It's one of the most misspelled words in the English language, although it's not
Wait,
used.
really?
Yeah, really.
Yeah. I'm still trying to connect to the internet on the Wi-Fi.
All right. There it is. Hi, Walter.
Hi, Mr. Douglas.
Okay, when you get settled, we have a quiz.
All right.
Well, I like what's written on your bag.
Oh,
I can see that.
oh.
It's good.
Yeah.
So Walter. It's quiz four, and the password is isosceles. Can you spell
Okay.
that?
Yeah, I can spell that.
Okay. Some people can't. you're done, guy. Walter, are you done?
Yeah, I'm done.
Okay.
I'm about to be done.
Okay. It's all right. You have some time. Walter, you are one fast typist.
Oh, thanks.
I could hear your keys. It's a useful skill. Okay. One more minute, Logan. Okay.
Okay. I just sent it in.
Oh, okay. Good. And Walter, you sent yours? Okay. Walter looks like he's having a busy day. Okay. Can you guys get on Adobe Connect? The Friday screen. And I'll remember to make you all presenters. Okay, Logan's on. Walter is on. Okay, good. Okay. Okay, I was going to have Ryan show his, well, I'll show it for him. So, I want to remind you that I'm in the process of making a test, the first test, and I am going to send it to your tech leads. And Walter, you've done this before, right? You had a test in the fall that your tech lead proctored. Yeah. And Logan, this is new for you, I think, right?
Yeah.
So I send it to Steve, right? He's your tech lead. Steve Orr, Mr. Orr.
Yeah.
Yeah. So I'll send it to him, and then you need to schedule a time with him outside of class. That's typically the way MSON tests are given, about an hour.
Yeah.
You need to schedule an hour sometime next week.
Okay.
All right. And he'll have that information. I'll send the test later today. I started it, but I'm not done yet. Okay. They're going to be 4 tests. I guess I told you that. And I put the schedule up on eCollege in the home, the course home. So you can check that out. All right. So I am going to share my screen. And let me do that first. Yeah, that's right. Okay, now I get it. I think. I have to do it twice. That's what I didn't realize. The first time it opens Adobe Connect, and then I share my screen and it gives me this. Yeah, that's why I was making the mistake the other times. All right. Now it should be shared, I hope. And I'm going to open Word. Let's see if you guys can see this. Can you see this?
Yes.
Yeah. Yes? Good. All right. So Logan, this is particularly for you because you said you had some questions on these proofs.
Yeah.
Okay. So, can you verbalize a question or tell me what part of it you didn't understand very well or not too clear on?
Well, I have like the idea of like what I'm trying to say, but like I'm not sure how to like the technicalities of what I'm trying to write down. I don't really know what to do sometimes.
All right. Let me just kind of go over it and see if that's helpful. And I'll start. And Walter, you can chime in and eat your lunch. This will give you a chance to eat your lunch too. So the key thing when we write this ebook, I don't like Theorem 3. You know, what in the world is Theorem 3? You have to look it up. But I remember that that's the theorem that says, and this is important, that you can, by one or two reflections, you can, or more generally by isometries, you can always map a segment onto a segment of the same length by and have the endpoints be where you want them to be. Okay, that's important. So, and the way you do that is you reflect one endpoint, let's say A, onto the desired endpoint, A prime, whatever it is, or C, whatever it is. So you match one endpoint by a reflection. And how do you do that? Can you tell me? How do you determine the reflection that'll map a point to a point?
You have to use the perpendicular bisector of the side.
Of the segment joining the point.
Yeah.
Right. Okay. So that's good. So now we're getting more precise with the words. And then you map the second point onto the second point by the perpendicular bisector. But you have to verify that reflection will keep the first point fixed, so it doesn't move. Right? And why is that? Why is that true? Why will that reflection? It would help to have a diagram, but why would that reflection have to keep that point fixed? And that's where the fact that the segments are the same length comes in.
Okay. Yeah.
So what's a characterization of the perpendicular bisector? It's the locus of all points, the perpendicular bisector of the segment joining two points is the locus of points that are, finish that sentence.
Collinear? Not collinear. I don't know.
Okay, that's one of the theorems, and that's really important. Walter, what is it?
Equidistant to both sides.
Equidistant to the 2 points, right.
Yeah.
So a characterization of the perpendicular bisector is all points that are equidistant from the endpoints of the line segment.
Yeah.
Okay, that's important. And since that first point must be equidistant because the segments have the same length, right? It must be on that perpendicular bisector.
Yeah.
Okay? So those are the theorems, those early theorems, 1, 2, 3. You may want to review those proofs, but that's the deal. And that's important. So we use that, what they call theorem 3 a lot. So now we know that we can always map one segment onto another segment so that the endpoints match the way we want them to. So that's the way this theorem starts. We map AB onto DE. So we match one side of the triangle. And that's what it says here by theorem 3. We can superimpose AB onto DE in 1 or 2 reflections. Okay?
Yeah.
All right. Now, if the third vertex matches, we're done. There's nothing to do, right? So if not, we need to reflect F across DE. All right. So if it's on the wrong side, we reflect it across. So because reflections preserve distance and angle measure, that's the important thing. So we always use reflections preserve distance, reflections preserve angles. We use that a lot, those 3-word reasons. So because that's true, C prime, that is the image of F, must lie on the ray because of which of those things? So when we reflect this A prime F in the diagram, it must lie along this ray F prime, A prime F prime, because what? Why do we know that when we reflect it, it'll lie across along the side of the triangle that we want? And not somewhere else, not somewhere here or somewhere here or somewhere else. What about the given information tells us that? Remember what we're given. We're doing side angle, side congruence.
Well, you have the angle measure.
Yeah, the angle measure, that's right. And reflections do what to angles?
They preserve it.
Right.
Yeah.
So it has to be on this line, right? But reflections also preserve what else?
Distance.
Distance, that's right. And so this segment length, so it has to be the right length, the right distance away.
Yeah.
Right? That's the side, side angle side.
Yeah.
We use this side, the first side, to match up, and then we use the angle to know that it'll fall along the right ray, and then we use the side length to say, okay, it's got to be in the right place.
Yeah.
Okay? All right. Is that helpful?
Yeah.
Okay. Yeah. Now, SAS is very similar. Down here, we match up. So you can read this again, but the idea is we match up the side, right? But this time we have the 2 angles here and here, right? So if F falls right on top, if it works, we're done. If it's on the wrong side, then we reflect. And since we're reflecting across DE, this segment, any point on the line of reflection is a fixed point. So those will stay the same. But now we have these angles, right? We have these angles. And so since reflection preserves angles, this is going to be along the proper side of the triangle, this ray, and this ray is going to be along the proper side of the triangle because of the angles.
Yeah.
So there are two lines, and one of our assumptions is that there's only one point where two lines meet. So it has to be the right point.
Yeah.
Okay? So that's
Got
the
it.
deal. All right. Hope that helped. Now let me ask another question. A quick question is there's another congruence method called side angle angle, which is the side is not between the two angles. It's just a side in any two angles. Okay? What theorem says that if we have side angle angle, then we have an angle side angle? In other words, we can reduce the side angle angle case to the angle side angle case. What theorem says that?
The sum of the angles is 180.
Yeah. Okay? Okay, Logan?
Yeah.
Yeah. So if two angles are equal, then the third angles have to be equal also. So two angles is enough. Okay. Did you? I haven't looked yet, but were you able to do an HL proof, Logan?
I sort of did it like this. I forgot what I did. I'll have to look at it.
Okay, I'll check it later. I was going to have Ryan share, but Ryan's not here, so I'm going to get up his, and we'll go through it. Okay.
Yeah.
So let me open that because I thought he was going to be here. And let's see, is this the? Was that the homework for? Well, let me try this one. Yeah, I got it. He won't mind because he did a really good job. Except it would be nice to have a diagram. So, can you see that? Here's what he says for HL congruence. And maybe I'll draw a diagram. That would be a good idea. So he says we're given these triangles, and AB is equal to DE, and we can superimpose the equal leg by one or two reflections. So let me use the shape thing here. I'm not going to save this. Let's see. Do we have a right triangle for a basic shape? Looks like we do. That's nice. All right. So let's see if we can do this. Yeah. Now there's a right triangle, but I don't want that fill. So format. And I don't want any fill at all. There we go. Okay. So there's a right triangle. And now I'm going to copy it and paste it. And I can, let's see, format. I think I can reflect it. Pretty sure. Yeah, here it is. So I flip vertical. There it is. All right. This is also a nice little review of how to use the word tools. I meant to flip horizontal. Okay, that was foolish. Let me take that over here. Undo. There. I want to flip it horizontally, not vertically. There. All right, so now we take this and move it over here, and we're going to match these, okay? So that's what he's done. Okay. Can you see that?
Yeah.
Okay. Now let's label. So let's make some text boxes here. So he did it so we can superimpose AB onto DE. All right, and B and E are the right angles. So I need to make all these letters here. Try to do this pretty quickly. A, yeah, so there's A. And I'm going to, let's see, I want to select that. There. Let me just select that. Yeah. I'm just going to copy and paste it a bunch of times. A, B, C, D, E, F. And then I want to change. Oh, let's spread them out. Okay. Sorry, it's taking a little bit of time, but not too long. I was hoping that Ryan would be here. Okay, well, A we got. I'm going to change this to B. I'm going to change this to C. This to D. This to E. And this to F. Okay. Now, we want to move this. So B and E were the right angle. So B is here. And so is E because we superimposed it. We'll put E right there also. And then AB. So A and B. Oh, I'm sorry. A and D. Wait. Yeah, A and D. A and D are in the same place here. And then C, let's say, is here. And F, let's say, is here. All right, now let's look at his proof, okay? So it says we can superimpose AB onto DE, which we did, with one or two reflections. We're done if, very similar, if F equals C prime. In other words, if the image, if it matches, we're done. If not, so this is now really C prime. This is what he calls C prime. Let's put a prime in there. Okay. He calls it C prime because we've reflected. We've moved it. So now, if not, we reflect C prime over AB. We'll reflect that. Okay. This would superimpose the two triangles. That's what he needs to prove, right? Because since B and E are 90 degrees, so these two angles are 90 degrees, right? So when we reflect, the reflection line is the perpendicular bisector. So it has to reflect along this ray, all right? They would form segment C prime F, right? But let's see. Now, by theorem 2, F and C prime are equidistant from D. So this is the equidistant business. So because the hypotenuses are equal, this point is equidistant from C prime and F, so it has to lie on the perpendicular bisector. That's the same theorem. So it can't move when we do that reflection. All right, so, and that means that this line is the perpendicular bisector of that segment, which means that that it has to map C prime onto F. Did I say that reasonably well, Walter? Or would you say it a different?
I'm not really following that well.
Okay, can you say it?
Yeah, so I got the part. It's pretty clear, like he can superpose AB onto DE, and then he reflects over that line. But I'm not exactly understanding how he can justify that C prime equals F after this reflection across the perpendicular bisector.
All right. Yeah. Okay. Let's see how we can say this. Since these are right angles, then we know that C prime will reflect along this line.
Yes.
Okay, so we know that. Yeah, let me say that better. Okay, so we know that it'll reflect along this line. The question is, will it reflect onto F? Well, the image of a reflection let's see how to say this. This has to be the perpendicular bisector because it's perpendicular and it's equidistant. This point is equidistant from, so it has to lie on the perpendicular bisector. So not only is this perpendicular to C prime F, but it's the perpendicular bisector. Therefore, since it's the perpendicular bisector, C prime has to reflect into F and not into something else.
Yeah. Okay.
Okay? Logan?
Yeah, I see now.
Yeah.
Is that really okay?
Yeah. I feel like it would be better to draw a circle centered at A with radius AF, and then you have the line intersecting. You have segment FC prime intersecting the circle in two places, and so the F has to be the reflection then.
Yes, I agree. I
feel like that would be. Okay.
Yes, I agree. Is that the way you did it?
I'm not sure.
Okay.
I don't remember what I did.
All right. That would be good if you had a chance to look at that and see if that's what you did. Okay, I'll think about this a little bit more, but I think we have the general idea. But you're right; it could be stated better. And Logan, you're right. It's hard to say these really well. It's not easy to give really tight proofs. So okay, but enough for now. Okay, so I'm closing this and I'm not saving it. Next, so I wanted to go over. Oh yeah, I wanted to define vector. And before I do that, I want to go here and get to this, because this is the equivalence class reading that we did, and this is an important but pretty abstract concept. So an equivalence relation has to have three properties. Remember what they are? Yeah. Okay. Logan, can you give me one of them?
No, I don't remember. Maybe.
Think about the properties of equality.
Is it like about the shapes themselves, or?
No. It's just any equivalence relation. Walter, what are they?
They're reflexive, symmetric, and transitive.
That's right. But let's review what those are. Okay. So what does reflexive mean?
So basically A equals A.
A equals A. That's right. Any object, any element is equal to itself. And then symmetric.
If A squiggly B implies B squiggly A.
Yeah. In other words, if A is equivalent to B, then B is equivalent to A. The order doesn't matter. And transitive.
And if A is equivalent to B and B is equivalent to C, then A is equivalent to C.
Yeah. Okay? And lots and lots of relationships satisfy that. So under examples here, give some nice examples. So, for example, if X is the set of all cars and this relationship is the equivalence relation has the same color as, then one particular equivalence class consists of all green cars, right? This quotient set, that they call it. In other words, the set of equivalence classes, which is what this is, could be naturally identified with a set of all car colors, right? So you could take a particular example of a green car. So we've sort of defined greenness that way by the equivalence relation of having the same color. And when you divide by that, when you just take the set of equivalence classes, then you have that situation. So here's another one, odd and even. You can say that the modulo 2 equivalence relation on the set of integers, if and only if their difference is an even number. Okay? So that gives exactly 2 equivalence classes, one class consisting of all even numbers and the other consisting of all odd numbers. So 7, 9, and 1 they're all in the same equivalence class. So one equivalence class is all even numbers, and the other equivalence class is all odd numbers. All right. Now going back to geometry, here, congruence is an equivalence relation, right? Because any triangle, for example, is equivalent to itself. If triangle A is congruent to triangle B, then B is congruent to A. And if A is congruent to B and B is congruent to C, then A is congruent to C. So when we take the quotient set of triangles under that equivalence relation, we get what?
Is that just a set of all triangles that are congruent to each other?
We get the set of triangle sizes and shapes. In other words, we no longer care if they're in different positions.
Yeah.
Right? So you can take you can take triangles and put them so that one vertex is on the origin and that a side is on the x-axis, the positive x-axis, and we're just looking at sizes and shapes of triangles. We no longer care where they are, because they're congruent. A congruence class, any element of that congruence class is the same. We can pick anyone anywhere, and so that's why we identify that. We've taken position out basically by doing that. Yeah. All right. That's a hard concept, I know, but there's an example. And I think that's the concept we want when we deal with vectors. Because any two vectors are equivalent. It doesn't matter where they are. We can put them anywhere. Right? If you move a vector, it doesn't really change the vector. If you slide it, you translate it. It's the same vector. So if we go back to Word here and go to definitions here, I think we're now in a position to define vector. Now, I haven't seen this. This is not common, but I think it's the way to precisely define a vector. So a vector is, I think a vector is an equivalence class. So I'll start it. An equivalence class of directed line segments. And you can, directed line segments under the equivalence relation. And what will be the equivalence relation?
Same size and direction?
Yeah. Equivalence relation as follows. Two vectors are two directed line segments, let's say. two directed line segments are equivalent if and only if, that's what IFF stands for, if and only if, let's use transformations. If and only if
one segment, if there exists a sequence of isometries.
Well, which particular isometry?
Translation.
Yeah. If and only if one is a translation image of the other. Does that make sense?
Yeah.
That means we can put them anywhere. All right? And there's a particular, I want to say this last thing, there's a particular element of the equivalence class that is used to, it's like a canonical, what we call a canonical form, a nice form. So in a coordinate system, where should we place the vector? So that, where should we replace all the vectors? Where should we place all the vectors so that we can compare them easily?
The origin.
The origin, that's right. So the canonical position is endpoint at the origin, beginning point, let me say, is beginning point at the origin. And this enables a correspondence between points in the plane and vectors. And that's where we get the notation of like 2, 3 for a vector that goes 2 to the right and 3 up. Right? So, for example, and I've noticed that Walter uses, and different books use different notation, so it's really, there's a lot of variance. But for example, so I'll say last thing. For example, three, and I don't use, let's do it right. Don't use it's not a good idea, I don't think, although some books do use parentheses, because that completely confuses it with a point. So 2, 3 is a notation for a vector that goes 2 units to the right, 3 units up. Okay. Now, when you study this, usually it's looser than this. It's not as precise. So this is the way I think in advanced math you would really make this idea precise. Okay, enough said. So that's our definition of vector, and I'll post that up. And I purposely didn't put. Okay, so now I want to know if there are any questions on the 3 reflections suffice. So I'm just going to get that up. Right here. All right. And this was an important theorem, and I'll add this to our theorem list. Any isometry is equivalent to a composition of at most 3 reflections, which is right away that limits our isometries. Are there any Walter, do you have any questions about this proof? Okay, Logan, do you have questions? If you do, ask them.
Okay. I'm fine.
You're fine. Good. Okay. So we'll let that go. That's an important thing. And then the next one was 1, 2, or 3 reflections. And the key thing here was So since 3 reflections suffice, we're looking at all isometries now, just in terms of reflections. So this already is pretty amazing to put these all down into one thing. So, and we're going to categorize all of every isometry this way. So case 0 says if an isometry consists of a single reflection, it's a reflection, obviously. And then 2 reflections we've done. The lines are either parallel or they're intersecting. And so I assume you were able to answer this. And then number 3 is describe, this was part of the homework, describe and sketch all the possible cases for 3 reflections. And it says there are a total of 4 cases for the configuration of the lines. One of those cases breaks down further into 3 cases, depending on the order that the reflections are performed. So, were you able to get 6 cases out of this?
Which was the one that broke down into 3 cases? I got the 4. Like you let the 3 lines be parallel. You have 2 of them be parallel, and then you have the 3 lines concurrent at a point, and then the 3 lines intersecting but not concurrent at a point.
Okay, good. That's a good start. Logan, did you understand that, or should we do it slowly?
Can we do a little bit slower?
All right. Can you say what you said again? Let me draw the 3 lines, and we can move them around. All right. So here's one line, and copy paste, paste. Okay. All right. Walter, say that again slowly, and I'll move the lines to illustrate. Walter?
All right. So I characterized the 3 lines by whether they were parallel or not.
Okay, so go ahead. So one possibility number 1 is?
So the first possibility is that all 3 lines are parallel.
Okay, so that's, stop. That's this one. Okay,
yeah.
Logan? Okay, next, second.
Oh, the second one is just 2 of the lines are parallel, and the third is a transversal, I guess.
Okay. Sorry, let me move just 1 point here. Yeah. So that's number 2. Draw, a drawing says a lot. Okay, go ahead. Third one.
And then the third one is where all 3 lines are concurrent at a point.
Okay. Okay. That's case 3. Okay, go ahead.
And then the fourth one is where, like, none of the lines are parallel, but the 3 lines still intersect with each other. So there are 3 points of intersection. Yeah,
right.
Like that.
Okay? Okay, Logan?
Yeah.
All right. Now, this is the case that breaks into 3. Into 3
Okay.
possibilities. All right? And it says, depending on the order that the reflections are performed. So let me label these lines with a text box. We're doing on time. I'm not going to do that because it's in the next the homework sheet. It tells you. So that's enough. I'm just going to close it and not save because I want to spend a little time, and we don't have much left. I want to spend a little time on the symmetry definitions because I'm going to give you more to do on that, 4 and 5. So, all right. So what's the difference between 2 and 3? In 2, you were to give all the symmetries of these various ones. Which one could you not give a symmetry definition for?
Trapezoid?
Yeah, trapezoid. There's no symmetry in a trapezoid. But other than that, you can give a symmetry definition. So let's take one example. Logan, can you tell me what symmetry an isosceles trapezoid has?
Reflection.
Yeah,
down.
And define it. Remember, you have to define it more specifically. So a reflection around a line, and you have to characterize the line.
Reflection through the center, not the center, but through the middle of the two bases, because the midpoint for the two bases should be on the same line.
Good. Okay.
That's where the line.
Right. So one could say, just like you did, a reflection across a line passing through the midpoints of the bases.
Yeah.
Right? That would be a way to say what you said. I'm trying to help you get the words.
Yeah.
Okay. Right. Can you describe for me, Walter, the symmetries of a rectangle?
Yeah, there are 2 lines of reflection, and these lines are the perpendicular bisectors of the opposite sides.
Okay. What else?
And then there's a rotational symmetry of order 2.
Yeah, a twofold rotational symmetry is what we say. And where's the point?
Oh, the point is the center of the rectangle.
Okay. And how could you find the center of a rectangle?
Oh, that's just the intersection of the 2 perpendicular bisectors.
Good enough. Okay, so something like that. And then the symmetry definitions differ because they're lean and mean, as I like to say. In other words, they are a minimal set. Okay? So for a rectangle, for example, Walter, what would be a symmetry definition of a rectangle? So a subset of the
a quadrilateral with 2 lines of symmetry, and rotational symmetry, and twofold rotational symmetry.
That's not minimal. We can do better than that.
That's not minimal.
Yeah.
Okay.
And in fact, you didn't define the lines of symmetry. You didn't specify them. So that's important.
So
yeah,
2
go ahead.
lines of symmetry that are the perpendicular bisectors of the opposite sides.
Okay. And one could be more minimal than that. Two lines of symmetry is good. You only have to say a little bit more about the lines of symmetry, and that will be enough.
They bisect the opposite sides?
Don't even need to say that. Because that's a consequence of something else, a consequence of the fact that they're lines of symmetry. You have to distinguish it from a rhombus, because a rhombus has 2 lines of symmetry also.
Okay, 2 lines of symmetry that go through the sides and not through the vertex.
Bingo.
Okay.
2 lines of symmetry not passing through vertices will do. That's enough. And from that, one can prove a lot of things. And incidentally, this is an important thing to point out quickly. If we know that the lines of symmetry are perpendicular, they have to be, and we should be able to prove that, actually. If we have 2 lines of symmetry that are perpendicular, and if you do 2 reflections in perpendicular lines, what's that equivalent to? What single isometry is that equivalent to?
A half turn rotation.
Yeah. So that's an immediate consequence of two perpendicular lines of symmetry is twofold rotational symmetry.
Oh, okay.
You know what I mean? So you got it right there. So that's why it has that. All right. So we're out of time. I was going to do 4A and B, but let me just say, given that kind of stuff, and what properties of these quadrilaterals are consequences of the symmetries? If we define quadrilaterals using these symmetries, what properties come out of that right away? So you have to forget the definitions, the usual definitions of a parallelogram, which is, two pairs of parallel sides, and you have to just use a symmetry definition. So before you work on this, I'll correct your homework and send it back to you so that you know what good definitions are, and then you use your definitions to do 4. All right? Enough said. I will let you go because we're out of time. All right. Have a good weekend.
Bye.
See you next week.
Bye.
You're welcome.
Wait. Wait. No. Stuff. Okay. Bye.
Bye. Close. All right. Stop the Still recording, although it stopped. Oh, confirm navigation, yes.